Hello students, this video is about quantum confined Stark effect and electro-optic modulators. In fact, this has another concept also which is known as Francekildish Effect. So let us see how all these three are related along with excitons. We have already seen a video on excitons. Let us see how all these are interrelated, right? Okay, now let us start. So you know about quantum well. Suppose I have a quantum well here. A quantum well is something like one dimensional box you have seen in the first semester, but that one dimensional box was an infinite box where the energy levels were not quantized. We then went on to a finite potential well where the energy levels are quantized. For example, you might have E1 here, you might have E2 here, and you might have E3 here. If I am trying to bring in E4, E4 will be out of the well. So which means this is a finite potential well, a quantum well, and it is quantized. Now this would be my conduction band, and I would have a valence band here. So you all know what a quantum well is. A quantum well is one semiconductor which is sandwiched between two different semiconductors, and there is a difference in their conduction band levels. That is what you see here. So these are my energy band levels in the valence band E1, E2 and E3. E1, E2 and E3, and transitions take place only between identical energy levels, which means there is a transition between E1 and E1, transition between E2 and E2, E3 and E3 and so on. You will not have a transition from E1 to E3 or E3 to E2 to E1 or whatever. So that is why energy band, which varies like this in the case of classical, will vary in steps. E1 to E1, then E2 to E2 and E3 to E3. This is how energy will vary in the case of a quantum structure. So this is the first thing you'll have to know. And we have already seen about excitons. So now let us take a quantum well, a small quantum well, which has only one energy level, E1, right? So I have my valence band as well, which also has only one energy level. You can draw it like this. I prefer drawing it like this, right? So this is what I have here. So now I have a quantum well in a semiconductor. So I have this piece of semiconductor here. Please remember, this is a piece of semiconductor. It is not a PN junction. So I'm biasing it. I'm giving a voltage to it. So you see there is a positive voltage here. When there is a positive voltage here, the electrons are attracted here. So when the electrons are attracted here, what happens is this, even whether it is a bulk, even if it is a bulk, now let me take a bulk material, the band structure. So when I have a conduction band and valence band like this, my bulk material will start tilting like this because of the overweight here. This is the energy band. Because of an extra weight here, my bulk band structure will tilt, but this energy level Eg will remain the same. This Eg will remain the same. The same is applicable here as well. Let me explain for the bulk material and come here. And now when this bends here, now suppose I have an electron here. Let me say I have an electron here. Now this electron, ideally, to make a transition to the conduction band, needs an energy greater than Eg. But now just project this electron. So if I project this electron, this will have a comparable energy level in the conduction band, which means theoretically this electron can exist in this conduction band, tunneling through this, because this is a forbidden gap. So tunneling through this electron theoretically can exist here or can exist here because the energy levels are comparable. Now let me come to this quantum structure. The same thing happens to the quantum structure when you are biasing it. So what happens to my quantum well is it bends. Same thing happens. My quantum well now bends. And this is what I see. By the way, this bending of bands And this possibility of electron existing either in the valence or the conduction band was discovered by these two people and hence named after them Franz. This is known as Francekildish effect. The bending of bands due to the application of a potential and the existence of electrons in the conduction band is known as Francekildish effect. Now you have this potential quantum well which is being bent like this because of Francekildish effect. Now remember, our exciton is here. In the case of a bulk material, an exciton which is here can break away and move away. But in the case of our quantum well, our electron will remain inside because of what is known as quantum confinement, meaning your electron can leave this well only if it has an energy greater than this barrier. So what happens? This electron exists here. That is the first thing. Second thing is, now I have, let us say, an electron here, and now because of the application of an electric field, this band structure is bent. Now I have a photon that is coming in. Let my photon have an energy h nu 1 such that h nu 1 is less than Eg. So your electron which is trying to go here, because h nu 1 is less than Eg, it cannot go here, but again it finds a place this side, which means there is a sideway tunneling and the electron can get in here. Though this is lesser than the band gap, the electron can get in here, which means you are going to get new peaks at lower energy, new peaks of energy at lower energy. So you have a situation where h nu 1 is less than the normal h nu, or you could say nu 1 is lesser than nu. So lambda 1 is greater than lambda, meaning the wavelength of the emitted light is high, or you say there is a red shift. Okay. Now this exciton which is trapped here is the main reason for these energy bands. Now you do not get one energy band, but you get multiple energy bands. Okay. So there is a splitting of energy bands, and you say what is happening here is Stark effect. Stark effect takes place in hydrogen atom. So here also there is a splitting of energy bands, and you call it Stark effect, but not just Stark effect, you call it quantum confined Stark effect. So what is quantum confined Stark effect? Because of Francekildish effect, there is a bending of energy bands. So now this electron, when it tries to go here, can get into the conduction band because of the bending. So you have electron which has lesser energy and larger wavelength. So there is a splitting of energy bands, and this is known as quantum confined Stark effect. So due to Francekildish effect, there is a bending of energy band. Due to quantum confined Stark effect, there is a splitting of energy levels, and you have wavelength which is now greater than the original wavelength. There is a red shift. So you say there is a change in the wavelength. So this, what is happening here is electro optic. This is an electro optic modulator, or you could also call it a quantum electro optic modulator. So what is an electro optic modulator? When applying an electric field, it brings about a change in the optical nature of the material, optical nature. It can be a change in the frequency, it can be a change in the wavelength or whatever. So here you see there is a change in the wavelength and there is a red shift. So Francekildish effect and quantum confined Stark effect lead to quantum electro-optic modulators. So Francekildish effect is the bending of bands, and quantum confined Stark effect is the splitting of energy bands, right? Okay, see you in the next video.